The analysis that we are going to perform are static analysis, modal analysis, that means natural frequencies and mode shapes, and transient analysis. This is a gravity dam that holds water by means of the concrete weight that conforms the dam. The dam structure is made up of several separated monolithic elements, as shown in this figure. These elements are separated by vertical joints. The contact types selected between the different elements and between the dam and the ground is for the touching contact type. Touching contact type means that they can be active or deactivated, touching or not touching. That's nonlinearity, causing the stiffness matrix to change. In the static analysis, the loading includes linearly increasing element surface pressures. As a result of hydrostatic loading, standard initial gravity loading is also applied, dead load. Civilfem users can perform a transient dynamic time history analysis considering joint behavior. That means geometric nonlinearity and the material nonlinearity. You can define several excitation functions by using time-dependent accelerations, velocities, or displacements in different directions. In this case, a time-dependent x displacement history has been entered into the foundation as a BC, boundary condition, simulating ground motion induced by an earthquake. We will now see this model in Civilfem. The tunnel is modeled as a 2D. After we do this model, we're going to see the third application as a tunnel into the, back to the second application. Now I'm going to open up the model and look at the gravity model. Now we can see the dam itself, which is soil. Then we see the model on the dam, cavity, a groove. Now we model using solid tetrahedra elements. Each one of these segments is making contact, the touching type. We can visualize the structure better if we could have the soil disappear as such. Now we can see the geometry. Now we can place the soil. As we stated before, we have different contacts, touching type. In this model, we have imposed some displacements. in 40 seconds. And this is the history of the displacement in 40 seconds. We can also visualize. Notice the distribution. The white the x displacement in red shows the applied known history. We can proceed to display the results. We're going to load the file with the previously calculated results. And we'd like to see the displacement variation response. At each time increment. In the first time step increment, we see the following displacement, deformation, in inches units, US customary. Now we proceed to the next step. We will see a greater displacement in the lower portion of the model. We continue the time history of the Z displacement, X displacement, I apologize. Now we can see this enormous mass of concrete, how it deforms, and best visualized by removing the surrounding soil. We continue the incrementing the X displacement that we have imposed. You can also notice how the soil has a perfect interaction with the structure. That is perfect compatibility. Now we're going to open the model analysis file. So we can see the different directions of model response. The natural frequencies that reciprocal will be periods of vibration and corresponding mode shapes. I'm going to load the first mode, which is a fundamental mode. Now we can see a table here. The frequency in hertz and the reciprocal, which is the period in seconds. So you could think of hertz as 1 over s. We only extracted or requested the eigensolution to provide the first 10 modes. Now we're looking at the second mode of vibration. Now we're going to see the third mode. Here we see frequency increasing. It's important to note that what we're looking for is that we want any type of dynamic loading to be far from any other natural frequencies of the solar structure system. We have also performed our analysis, static analysis, where we have applied the hydrostatic pressure. Now we'll see the applied hydrostatic pressure on the dam in the lower portion of the model. Now we can see the response to such loading. As easily as we can see the displacement response, we could also see the loads. We can see where a canopy would crack, amongst other results.